Everyone knows black holes, cosmic monsters so powerful that nothing, not even light, escapes. These enigmatic objects have fascinated scientists and the public alike for decades, representing the ultimate extremes of gravity and the limits of our understanding of physics. But what if the same equations that predict these prisons also predict a twin, the white hole? While black holes are famous for their inescapable pull, their theoretical sibling is just as intriguing, yet far less understood. The mathematics of general relativity doesn't just allow for black holes, it also hints at the existence of their opposites. Imagine a place that violently expels everything, a cosmic geyser erupting matter and energy. Instead of swallowing up everything in its path, a white hole would be a region of space where nothing can enter, but everything inside is forced out in a spectacular display. If a black hole is a destination with no exit, a white hole is a source with no entrance, it's a mirror image, a cosmic reversal of everything we know about black holes, challenging our intuition about how the universe works. It's the black hole in reverse, a singularity exploding outward, not collapsing inward. The very laws that describe the crushing gravity of a black hole also allow for this explosive, repulsive phenomenon. This isn't science fiction, it's a real solution from Einstein's general relativity. The equations are elegant and precise, suggesting that white holes are just as possible as black holes, at least on paper. Yet the universe seems to have other plans. Yet when we look to the cosmos, white holes are conspicuously absent. Despite decades of searching, astronomers have never found definitive evidence of a white hole in the observable universe. Why does the universe favor black holes? Are white holes just mathematical ghosts? Or could they answer deep questions about time and information? Some physicists wonder if white holes might hold clues to the mysteries of the Big Bang, or even the fate of information lost in black holes. The story of the white hole pushes us to the edge of our understanding, challenging our ideas of beginnings and endings. It forces us to confront the limits of our knowledge and the strange possibilities that lie beyond. The silence where white holes should be is an invitation to look deeper and question everything. Perhaps somewhere in the vastness of space the answer is waiting to be discovered. The idea of a white hole is one of the most fascinating and mysterious predictions to emerge from Einstein's general relativity. It's a concept that seems almost ghostly, an object that, according to the math, should exist, yet has never been seen. In 1915, Einstein's revolutionary equations redefined our understanding of gravity. Instead of being a force, gravity became the warping and bending of space-time itself, caused by the presence of mass and energy. Not long after, the brilliant physicist Carlo Schwarzschild found a solution to these equations. His work described what we now call a black hole, a region where gravity is so intense that nothing, not even light, can escape its grasp. At its heart lies a singularity, surrounded by an event horizon, the ultimate point of no return. Decades later, mathematicians Martin Kruskal and George Sekeres took these ideas further. By mapping the full structure of Schwarzschild's spacetime, they uncovered something astonishing. The same equations that describe a black hole also predict the existence of a white hole, the time reverse of a black hole, where nothing can enter, but matter and energy can only escape. In this elegant mathematical model, matter falls into a black hole in one region of spacetime, while in another, it is expelled from a white hole. The two are connected in a way that seems almost like science fiction, a cosmic bridge between regions with matter flowing in and out. The Kruskal-Sekeres diagram reveals four distinct regions: our familiar universe, a black hole, a parallel universe, and a white hole. It's a map of possibilities, showing how these exotic objects might fit into the fabric of reality. The mathematics is undeniably beautiful, weaving together black holes and white holes in a perfectly symmetrical dance. But there's a catch. These solutions describe eternal objects, black holes and white holes that have always existed with no beginning or end. In the real universe, things are born and things die. Stars collapse under their own gravity to form black holes, a process we've observed in spectacular cosmic events like supernova. This process of black hole formation is messy, violent, and rooted in the arrow of time. It seems to rule out the existence of pristine, time-reversed twins, white holes that have always existed, spewing matter into the cosmos. So, while the mathematics of general relativity allows for white holes, the universe we observe may not. The symmetry is there in the equations, but nature seems to prefer black holes with beginnings, not their eternal, ghostly opposites. The question remains, are white holes just beautiful artifacts of the math, haunting the edges of our understanding, or could they one day reveal themselves in the depths of space? A black hole's event horizon is a one-way boundary. Nothing escapes. A white hole's horizon is the opposite. Nothing can enter. Matter and light pour out, but nothing from outside can cross in. Even a photon hurled at a white hole would never reach it. Time dilation stretches the journey to infinity. You could observe a white hole's mass and spin, but never interact with its source. It's a cosmic ghost, affecting its surroundings, but untouchable. While black holes are perfect absorbers, white holes are perfect emitters, erupting without cause. This causelessness is deeply troubling for physicists. Everything in the universe has a history, a chain of cause and effect. A white hole would simply exist, a creation event with no past. That's why in the classical world, white holes seem impossible. They violate our most basic intuitions about how the universe works. Einstein's equations may allow white holes, but physics resists them. The second law of thermodynamics says entropy always increases. Time moves forward, not backward. A white hole would mean a sudden decrease in entropy, like smoke reforming into a log, statistically impossible. Even if a white hole formed, it would be unstable. The universe is filled with radiation. Even a single photon trying to enter would trigger a catastrophic collapse. The white hole would instantly become a black hole. Its defining feature, no entry, ensures its own destruction in a real universe. White holes can only exist in a perfectly empty, idealized cosmos. In reality, their fragility makes them vanish the moment they meet the universe. That's another reason we don't expect to find them. There's a clear recipe for black holes. Massive stars collapse, gravity wins, and a black hole forms. This process is natural, predictable, and observed. Black holes are the universe's ultimate endpoints, increasing entropy. But what about white holes? There's no known process to create one. They'd require a singularity to suddenly explode outward, something we never see. The Big Bang was the expansion of space-time everywhere, not a local explosion. White holes would be little bangs with no cause or history. In a universe governed by cause and effect, objects that appear from nothing are deeply problematic. Black holes are natural, white holes are cosmic orphans appearing only in math. Nature knows how to make black holes, but not their twins. That's why white holes remain theoretical oddities. For decades, white holes were just mathematical curiosities. But quantum gravity, especially loop quantum gravity, LQG, offers a new perspective. LQG suggests space-time is made of tiny loops, with a limit to how much matter can be squeezed. Instead of a singularity, a collapsing star forms a Planck-star, a tiny, ultra-dense object. Some theorists propose that this Planck star eventually bounces, reversing collapse and expelling matter. From the outside, it would look like a black hole transforming into a white hole. This process has a cause, the original collapse. It could solve the information paradox. Information isn't lost, just delayed and then released. Extreme time dilation means this bounce could take billions of years from our perspective. A black hole today might not become a white hole until the far future. If black holes can become white holes, we might detect them. The bounce would unleash all the black hole's mass and energy in a brilliant flash. Some theorists suggest gamma-ray bursts, GRBs, could be white hole signatures, especially from tiny primordial black holes. As these evaporate, they might bounce and release energy as gamma rays. Fast radio bursts, FRBs, brief, powerful radio flashes are another candidate. A black hole exploding as a white hole could generate such intense bursts. Astronomers search for unique patterns in these signals as possible evidence. Some theories even link white hole remnants to dark matter, tiny, stable objects left after the bounce. If primordial black holes were common, their remnants could account for dark matter today. The search continues, but so far, these clues remain tantalizing hints. The white hole divides the physics community. Most astrophysicists see it as a mathematical ghost, barred by thermodynamics, instability, and lack of formation. The Schwarzschild solution describes eternal black holes and white holes, not real ones formed by collapsing stars. In this view, white holes are artifacts of idealized math, not real objects. But quantum gravity theorists argue white holes are inevitable, solving deep paradoxes like information loss. They claim the bounce is a quantum process, outside classical rules. The debate highlights attention trust established physics or follow bold new theories. Skeptics want evidence. Proponents see theoretical beauty as motivation to search. For now, white holes exist between a no from classical physics and a maybe from quantum theory. The white hole remains one of science's most captivating enigmas, a cosmic riddle that has fascinated physicists and astronomers for decades. Unlike black holes, which have been observed and studied, white holes exist mostly in the realm of theory and imagination. Born from the same mathematical equations that describe black holes, the white hole lingers at the very edge of our understanding, challenging us to rethink what we know about space and time. It's a concept that pushes the boundaries of physics, inviting us to explore the unknown. Most physicists doubt that classical white holes exist in our universe as their properties seem almost too fantastical. Yet, quantum loopholes and new theories keep the possibility alive, fueling ongoing debates and research in the scientific community. The idea that a black hole could one day bounce into a white hole suggests a cosmic cycle of collapse and rebirth, a universe where endings are not final but instead lead to new beginnings. This theory hints that information swallowed by black holes isn't lost forever, but may be preserved and eventually released, perhaps in the distant future, through a white hole's outburst. Every new cosmic burst detected by our telescopes is a potential clue, a chance for discovery. Scientists scan the skies for unusual signals, hoping to catch a glimpse of something that could confirm these bold ideas, though no signal has been conclusive yet. The absence of evidence isn't evidence of absence. We are only at the beginning of our journey to probe these deep cosmic mysteries, and the universe may still hold secrets beyond our current reach. The universe is full of surprises, often stranger than we can imagine. Each new discovery challenges our assumptions and opens doors to even more profound questions. The story of the white hole is a testament to human curiosity and the power of mathematical imagination. It reminds us that even the wildest ideas can inspire real scientific progress. Whether white holes are real or remain forever theoretical, they push us to ask deeper questions about time, the universe, and the very nature of reality itself. They urge us to keep searching, to keep wondering. As we gaze into the cosmos, we remember, wonders may still be hidden, waiting for us to find them. The frontier of cosmic inquiry is vast, and our journey has only just begun.